Hello, I'm Tobias Landwehr, and I will first give a few short comments on our efforts on diarization for meeting scenarios, and then we will start into the separate presentations. Yeah, so we worked on the diarization for meeting scenarios, and that means that we want to apply the diarization directly onto a session recording before doing the subsequent stages like speech extraction and recognition. Diarization describes the problem of who speaks when, and because we want to apply it directly onto the meeting scenarios, we need an explicit support of overlap and need to be able to handle arbitrarily long sequences of speech. Therefore, we can't use Therefore, we can't use the classical approaches like I vectors or X vectors directly. These approaches refers to a segmentation of the meeting session and then extract an embedding for each of these segments. Then these embeddings are clustered to assign one speaker to each of these segments. So these classical approaches like I vectors or X vectors are not able to handle overlap. So we researched 3 different methods during this workshop. First, Zili will talk about region proposal networks and clustering, where the overlap issue is solved by a segment-wise diarization, but these segments are jointly estimated with the speaker embedding. First, Zili will talk about the region proposal networks, where the overlap is handled by a jointly segment estimation and speaker extraction. Then Thilo and I will talk about block online neural speaker diarization for long recordings, where we handle the overlaps through a frame-wise classification. And Thilo will present a speaker tracking module that is able to keep the speaker information over multiple blocks. And then finally, Zumi will present an end-to-end speaker diarization with the transformer architecture, where we also have frame-wise classification, and it jointly uses frame-wise the local and the global information to handle the diarization problem.
So I will introduce the region proposal network-based speaker diarization, the RPNSD. So this work is inspired by FastRZN framework, which is one of the most famous framework for object detection. So the pipeline of RPNSD is kind of similar to the traditional pipeline. However, unlike the traditional pipeline, instead of cutting the speech regions into multiple short segments and making decisions on each of them, we are directly predicting the segment boundaries for each of these segments. And also, the traditional pipelines has several individually optimized modules like the speech activity detection, embedding extraction, and the resegmentation. However, the RPNSD system is jointly optimized. And the RPNSD system mainly has 2 advantages. The first is that since the proposed speech segments can have overlap with each other, so this system can handle the overlap speech. The second is that unlike some permutation invariant training-based system, our system can handle an unfixed number of speakers. And the whole pipeline can be roughly divided into 2 parts. The first part is the joint speech segment proposal and the embedded extraction part. The second part is the post-processing part, which includes some clustering and non-maximum suppression. So we will take a deep look at the first part, which is the core part of this system. So the input to the first part is the extracted STFT magnitude, and the output will be the proposed overlap speech segment proposals together with the corresponding speaker embeddings. And there are mainly 4 steps for the first part. The first, we will extract some feature maps with the convolutional neural networks, and then we will predict the speech segment proposals with the region proposal network, which is shown in the following figure. So the basic idea is that we will consider each time step as a possible center, and we will expect several bounding boxes with different sizes from the center. And we will compare these segments with the ground truth label. If the segment is quite close to one of the ground truth labels, then we would label it as positive. Otherwise, we will label them as negative. So in this way, we will convert the problem of predicting the speech segments to a binary classification problem. And after we predict these overlap speech segment proposals, we will pull out the deep features with a pulling method called ROI line. And finally, we will perform speaker classification and boundary refinement on the top of these pulled features. So in this workshop, I conducted the experiments on both simulated dataset and the real Libriscss dataset. And in this presentation, I will just report the results on the Libriscss dataset since it's more close to the real scenarios. So in this table, we compare three different systems. Our baseline system is the X vector plus the spectral clustering systems. It achieves 90% diarization error rate on the dev set and 18% on the evaluation set. As a comparison, the region proposal based diarization system achieved 8% on the dev set and 9.5% on the evaluation set. Although the performance is not as good as the TSVAD system, which achieves better performance, but our system doesn't have any dependencies on some other system. And also, it is possible to use the region proposal-based diarization as the initialization for the TSVAD systems, which might improve the performance. And also, we observed that the improvement from the diarization also benefits the ASR part. So on the development set, the word error rate decreased from 32% to 26%, and on the evaluation set, it improves from 31% to around 29%. So we also analyzed the diarization error results for different overlap ratios. So as you can see from this table, as the overlap ratio increase, both the X vector system and the RPN-SD system will have some degradation. However, it seems that when the overlap ratio is higher than 20%, the region proposal-based diarization system is much better than the X vector system with spectral clustering. And we may also take a look at the DER decomposition. It seems that most of the improvements comes from the reducing the miss rate. Due to the ability to deal with the overlap, due to the ability to deal with the overlap speech, the RPN-SD system can largely reduce the miss rate by 10% at the cost of slightly improved false alarm rate. And for the speaker confusion, both systems perform almost the same. And so here is the conclusion. So the region proposal-based diarization system can improve the performance by predicting better segments. And in the future, we will also try to add different weights for different segments, since some of them are, we think that some longer segments might require larger weights. And now let Tobias and Thilo will introduce some frame level based diarization system. Thank you.
Thank you.
There was a question from Ivan, which is generally applicable to all of you and even the previous talks. He asks, do you have the DER broken down by different overlap ratios for TSVAD? maybe we can take this later if Markui or somebody has the answer.
Yeah.
I don't know if you guys do.
Actually, I don't have, but I think Maokui will have answers to this question.
Okay, so you guys continue and we'll come back to Markui afterwards.
Okay. So I also see another question. Did you use TS-VET on the top of X vector base or on the top of? Also, I was using the TS-VET on the top of the X vector plus spectral clustering. Yeah.
So here, Tobias and Tilo investigated this block online neural speaker diarization for long recordings. And maybe next slide.
I'm trying to. There it goes.
Okay, thanks. So there are several methods that can deal with overlap speech in a way slightly different from this region proposal network. And here we focus on a method that directly estimates diarization results through classifier as denoted in here. And here, this method that is listed on that is denoted on the left-hand side can naturally handle overlaps by directly estimating the diarization results, but it can deal with only the fixed number of speakers. That's a drawback. And recently, to alleviate this problem, an extension of this approach was proposed. And now the extension uses this encoder-decoder type of architecture and estimate variable number of attractor. Attractor can be interpreted as a centroid of speaker embedding vectors. And now it can deal with variable number of speakers. But both of these approaches needs like a full access to the entire meeting data. That's one of the drawback. And quite often, meeting data is long, like 1 hour long, and it's not really sometimes feasible to process such a long meeting data in a batch mode. So, and we sometimes have to resort to block online extension. So here, next slide, please. So here we propose this block online neural speaker diarization. And it comprises basically two parts. First part is this conventional encoder-decoder based neural diarizer that can perform locally diarization within each block. And it performs in each block diarization. And while it is performing diarization, this speaker tracking module can basically model long-term dependency by appropriately managing speaker embedding vector. And importantly, this entire model can be jointly optimized since both of them are modeled or formulated in completely neural network. And I'm going to, I first explain this encoder-decoder diarization investigation part. This was done by Tobias. And basically, we first implemented this conventional neural diarization method and tested it on Librispeech data and found that it works to some extent, but it seems that we still need some careful fine tuning or maybe some parameter tuning. And that's kind of the to-do thing. But yeah, and that's the status that we are in for this module. And then maybe Tilo, you can take over.
Okay, so the second part of this proposed method is a speaker tracking module. And during the workshop, I worked on that. And typically, such a speaker tracking is tackled with some sort of clustering. So we can use an offline clustering algorithm that uses like k-means that uses all embedded vectors from a whole utterance. They can perform a globally optimal clustering, but they don't allow any online processing because they need all vectors from the utterance. Or we can use online clustering that keeps some sort of state and then update the state and the output diarization or clustering every time a new vector comes in. And these often have problems with recursive updates. So if they do one wrong update, everything that follows is faulty. And often they have problems with long speaker inactivity and loose speakers in that case. And our goal was to improve over this by proposing some optimal clustering of the speaker embedding vectors in an online manner, and by estimating the number of speakers, and also to allow joint optimization with other neural network modules, such as diarization or separation that model only a segment of speech data. And like a perfect fit for such a system is a neural Turing machine. And its format is okay, but it has a persistent external memory that stores speaker embeddings of the speakers that it has seen so far in the recording. And when a new speaker vector arrives, it reads the available information for that speaker from the memory. And if it's an existing speaker, it updates the memory with the newly available information. And if it's a new speaker, it allocates a new memory cell. And by doing this, we assign each speaker a unique memory address and are able to track them over very long time ranges. We can count the number of speakers by counting the total number of used memory addresses, and we can use the accesses to the memory addresses as a diarization result. The system is still under development, but I still want to show you some results on a toy example here. So I generated simple sequences of speaker vectors with 2 to 5 different speakers per sequence and fed them into the system, and then used the memory accesses as a diarization result. I compare this with the leader-follower clustering, which is a simple clustering algorithm, online clustering algorithm. We can see that here, depending on the memory initialization, the Turing machine is close to the leader-follower clustering in terms of both the diarization error rate and the source counting accuracy. And if we initialize the memory with random speaker vectors from the training data before processing a sequence, then the Turing machine achieves a better counting accuracy on noisy data than all other systems. And the noise that I added here on the experiments on noisy data is simply white noise. So overall, these simulation results show that the system works in general on this toy example, and that it's worth to investigate it further. And our further work on this topic will be concentrating on training the EEND system on meetings with more speakers and to implement this blockwise processing. And the neural Turing machine will continue experiments there on more realistic data like Librispeech, and also test more advanced memory architectures to prevent these recursive update problems that still sometimes occur in this memory. And the final goal is joint training of both modules to obtain an optimal system for diarization block online manner. Okay, thank you. And the next talk will introduce another method for end-to-end neural diarization.
Hi, I'm Shomi, and this is a joint work with Hakan and John. Next. Our approach towards end-to-end neural diarization is to use a local global modeling. For a local model, we want to use a model that can work similar to an acoustic model and generate local features. We use a convolutional neural network for this local model, and the global model could then utilize these features and do a global processing to refine the results for diarization. We propose to use a transformer for this global model. Of this both local and global model we train in one session as an end-to-end manner. We compare our model with 2 baselines that uses one model for diarization directly, a BiLSTM and a transformer. Next, please. For end-to-end diarization, we take the input mixture and we are predicting per source, per frame, a binary activity. So in a way, we are trying to predict this kind of binary image of whether the speaker was active or not. On our models, we apply binary cross entropy with permutation invariance. The diarization labels are generated at a rate of 10 Hz, and we train on 90-second meetings. Next, please. As a local model, we propose to use a TasNet-like model. This is more similar to the TasNet separation block. It's a temporal dilated convolution model that uses multiple 1D dilated convolution blocks where the dilation increases per layer exponentially and then starts from 1 again. Input to this TasNet is input mixture STFT, and the output is fed to a linear plus sigmoid layer for predicting diarization probability. Next, please. As a local model, TasNet can generate an embedding, and then we can utilize a transformer to refine the embedding produced by the local layer for better diarization. We hope that a self-attention can do better for context modeling and give us better results. So in case of local global model, we use TasNet and transformer and apply a BCE loss on top. We can also use two losses, one on the local model, one on the global model, to make both model learn embedding that are useful for diarization. Next, please. We compare our local model with a model that has LSTM as a global model instead of transformer. We test our models on an internal dataset. This dataset looks like a conversation and generated from a speech from Librispeech. There are variable number of speakers, 1 to 5. If a speaker is missing, we just pad the speaker with all zeros. The speaker is speaking maximum of 2 times. That's the constraint. We are working on trying to remove that. With this setup, we get 90-second example meetings with around overlap 7 to 15%. The data set is mixed dynamically, and that gives us access to a very large training set. Next, please. We test on our internal data set and measure frame-wise diarization error rate. We see that just using BiLSTM or transformer gives us a DER of around 30. Using BiLSTM as a global model also does not improve much. Using just the local model actually does better DER of 12. And adding a transformer on top improves, especially when we can add an iterative loss, we get a DER of 6. Next, please. We also tested our model on SimLibricss with 4 speakers. There were around 40% overlap, and the speaker were 3 to 4. This dataset is on 120 second examples, and we have training data around 100K. On this model, our local model achieves a DER of 13, and the local global model achieves a DER of 12. Next, please. On another SimLibricss with 8 speakers, we observe worse results. In this data set, we have variable number of speaker maximum 8, around 20% overlap. Overlap is less than the previous one, but the speaker is more. But we have also 18K training meetings, and then there is no dynamic mixing. On this setup, we see both of our models, local and global, are overfitting, and we achieve a DER around 20. Finally, to conclude, we are working on, it seems, amount of training data helps us a lot. So we are working on adding dynamic mixing to SimLibricss conversations. We're also working on improving our internal conversation data set so that a speaker can speak more than 2 times. And finally, we want to see if either local or global or both models can incorporate speaker loss for better diarization.
Sumit, Paula asks a question. It's in the chat. She says, do you have the decomposition of the DER into misses, false alarms, speaker errors?
I do not. I'll try to get those, definitely. Just from example, it seems there are more miss than other errors, but it'll be good to have numbers.
Okay, thanks.
I think there's another question for Thilo, right?
Yeah, there's a question for me. And it's how NTM handles the appearance of previously unseen speakers. Yeah, the addressing to memory works with a similarity. So if there's a new speaker that is not in the memory, then these similarities become small. So the network can easily detect this if the vectors are clean enough. And then it can write to a new memory cell. And this is done with a least used addressing. So it's written to the cell that's least used in the memory. I hope that this answered the question.
Yeah, I think it did.
Okay, so is there any other questions? Okay, then let's move to Then let's move to the next talk on this meeting-wise speech separation. Yi, are you there?